Welcome to Curve Sketching Weekly Work Part 1. This is a homework help video, and I think you'll find this to not be a very difficult homework, and certainly if you watch the video you should be okay. Alright, so first of all, EVT, we're finding absolute maximum, absolute minimums. Here are our steps. So first, check that the function is continuous, because there's the only way that you can guarantee you have an absolute max or an absolute min is that the function is continuous on the interval. Right? So, and then say why that function is continuous. Right? Don't just look at it and go, yep, continuous, without making sure you explain. All right? Make sure you include that. All right? So these functions are continuous everywhere. And it's fine to say this function is continuous on the interval because such and such a function is continuous everywhere. And functions that are continuous everywhere are polynomial. That, of course, includes quadratic and linear. Exponential. Sine and cosine. And then other functions within their domain. So logarithmic within the domain. The radical functions, odd, I have to keep going here. Odd roots are continuous everywhere. Even roots on domain. I don't know why I put W here. On domain, with domain, that doesn't make any sense. Even roots on the domain. All right, so if you can't plug the value in, you can't have you can't take the square root or fourth root of a negative number and have it be a real number. And then rational and the other trig, except at asymptotes. And for the rational, this took me more space than I thought. Oh, actually, I can just move this down. Except at points of discontinuity and asymptotes. Yeah. And asymptotes. All right, so if there's no asymptote in the middle of the interval or a discontinuity, it's in the domain of the function, then the function is going to be continuous. So this is continuous everywhere, are these ones, and also here I'll put odd roots over here. And this is continuous on the domain. All right. So that's how you can justify whether the function is continuous. That's step one. So verifying it's continuous is step one. I'll just put big old 1. That's all 1. Step 2, define critical points. You find the derivative. And set the derivative equal to 0 and solve. All right, those are your critical points. All right, so then you evaluate the function at the critical points and the endpoints. So, for instance, for the first one here, you would find f of 0, f of 2, and then f of x such that f prime of x equals 0. All right? So once you find out where those critical points, you evaluate the function for that. And then identifying the absolute extrema, who's the biggest, who's the smallest? That's all there is to step 4. All right, so step 4, identify largest. Of course, that's your extreme max, and smallest. And these are your absolute extremas. And that's all there is to it. That's it. Right? So if you can find a derivative and set it equal to 0 and evaluate functions, you can, and make sure you verify continuity on the interval, you can find the absolute max and min. All right? So that's all there is to this one. Next set. All right? So first derivative test in monotonicity. You're finding the critical points. All right? So exact same thing as before to find the critical points. This is the critical points for the first derivative. Take the first derivative. And set equal to 0. To find your intervals of increase and decrease, you then make a sign chart, right? So this is the first step, right? And that's how you find your critical points. And then, so that's step 1. And then for step 2, justify intervals of increase and decrease. Where am I going to put step 2? I'll put step 2 right here. So I don't really need the problems per se. And then for step 2, you make your sign chart. So for the sign chart, you have your critical points, right? And those were the values of x where the first derivative was 0. Also where the first derivative is undefined. Right, so any of these are the critical points. Right, there may be some undefined. I'm looking at b, that's a rational function. Right, could be undefined. Likely, very likely will be undefined somewhere. And so those are your critical points. And then maybe you've got several. Let's say there's 2. Looks like most of these will have 2. And then you evaluate in between those, right? And you determine the sign. It doesn't really matter what the value is, it just matters what the sign is. And then you evaluate it in the derivative, right? So you'll pick a value that's less than your smallest critical point. You'll pick a value in between the critical points, and it doesn't matter what value, just pick the one you like the best. And then of course, you'll pick a value that's larger than all your critical points, and you'll plug those into the derivative, right? And you'll look at the sign. Is it positive or negative? And right up here, I have a little chart to remind you. All right, so if f prime of x is greater than 0, the function is increasing. If the first derivative is less than 0, the function is decreasing. And you have all this in your notes. This was taken literally from the notes. Hey, it's writing pretty straight. It's not writing in the right spot, but it's writing pretty straight. Any helpful hints on these? I'm going to give you a little helpful hints. Helpful hints right here on the derivatives. I didn't on the other one because, well, they weren't that, well, this one is a product rule. I will give you a little helpful hint there. And this one is simply a power rule, but rewrite that 3 over x. You don't have to use the quotient rule for that. Here you've got a product rule, power rule, quotient rule. Oh, and a hint. I'm giving you a hint here. Actually, well, on taking the derivative, just take the derivative, but I wouldn't bother to change this. But you may want to change something when you go to solve. It'd be easier if you don't have a sine and a cosine in the same equation. You could even change it now. So if you're finding the derivative just as the equation is, you're going to use a chain rule for that. For the sine squared theta, I trying to remember if I don't remember if I changed it. You could technically use Pythagorean theorem and change the sine to a cosine. I don't know if that will matter that much, and maybe it'll make it easier for the solving, changing it before you take the derivative rather than afterwards. But you could use Pythagorean identity if you like to change the sine squared theta. So you don't have any, you have all the same trig function when you go to solve that first derivative. Right, so just a thought. All right, and so that's all there is to these. And by the way, I do have power hour. I have open office hours starting next week, and so you can drop in or just email me if you have questions on any of these. All right, Rawls theorem, mean value theorem. Apply the mean value theorem to the interval indicated. Make sure the hypothesis is true, and then find all values in the interval guaranteed by mean value theorem. All right, make sure that you are justifying. All right, on the AP test, you'll need to justify. If you just go and find the values and you never say step 1 and step 2, the function's continuous and the function's differentiable and why, right? Then nobody's going to read on to the rest of it. All right, you have to verify that the requirements are met. All right, so make sure requirements are met. And explain. It doesn't have to be a long drawn-out explanation. In terms of continuity, same thing as before, right? Continuous on the closed interval, right? So the same functions as we had before over here are continuous, right? The ones that have discontinuities, rational and trig functions, right, at asymptotes, points of discontinuity, just make sure there's none in the interval, right? And then even roots, just make sure, even roots and, oh, log didn't belong over here. Look at that. I've got, let me fix this, because I should switch these. Log belongs with the continuous on the domain group. Odd roots are continuous everywhere. Log is only on the domain. Y is continuous everywhere. No, not X. Can't just plug in negative numbers there. All right, so the same rules for continuity apply. Differentiability, got to be continuous. So if you've, now, differentiability implies continuity. If it's differentiable, it is continuous. But just because a function is continuous does not mean it's differentiable. There also has to be no corners, cusps, of course no asymptotes, but an asymptote is a discontinuity. I forgot anything else. Well, if it's continuous, the ones to look out for are corners and cusps. But who's going to have a corner or a cusp? Right? It's going to be a piecewise function. Right? So there's no piecewise functions here. Right? None of these three are piecewise functions. Oh, almost forgot. Vertical not vertical asymptotes, vertical tangents. That's what I was trying to say. Right. So can't be a vertical tangent. How will you know you have a vertical tangent? 0 in the denominator of the derivative. Right. So if you take the derivative and you got a 0 in the denominator, that's a vertical tangent. All right, so those are the things that would make it not differentiable. But really, so long as it's continuous, chances are just verify the rest, and then you'll be fine. And the corners and cusps, those occur only in piecewise functions. Regular functions just don't have corners and cusps in the middle of it. Once you've done that, you find f of a and f of b. That's in the original function, right? So, for instance, if you were doing a here, you would find f of -1 and f of 1, so long as the other two have been met. Now, if the other two aren't met, you would just explain why mean value theorem does not apply. Right? But if a and b, if steps 1 and 2 are met, then you go right to step 3. You find f of a and f of b, and then you find the slope of the secant line, which is the average value, not the average value. I have that same typo from the lesson, and not average value. Average rate of change. I don't know what I had in my head when I wrote average value. Average rate of change. Average value is something completely different. Doesn't even use the derivative. Average rate of change. I think that's the only place I've got average value instead of average rate of change. So you find the average rate of change, which is just slope, right? It's just the slope between the line that would connect the 2 points, right? So you find that. Then you find the derivative. You set the derivative equal to the average rate of change. Let me fix in this lesson. Average rate of change of the secant line, and then you solve for x. So what you do is you are going to, after you find the average rate of change, you're going to set the derivative equal to the average rate of change. So this is the derivative, and solve for x. Right? So it's just like instead of setting the derivative equal to 0, right, because a horizontal tangent would have a slope of 0, you're setting it equal to whatever the slope of the secant line is. All right, and you're solving for x. That's all there is to it. All right. Curve sketching, it's not really, once you got the steps down, it's not really too difficult. Rawls' theorem is very, very similar. There's only one difference. So I won't go through every single step again. You're still going to check the functions continuous on the interval, check the functions differentiable on the open interval. Why it says closed interval, by the way, an open interval. So the endpoints have to be continuous. The endpoints aren't going to be differentiable, so that, you don't have to worry about that. So it's the closed interval because endpoints must be continuous too. So it means there's brackets and not parentheses. All right, so same things for 1 and 2 there. All right, but then that's where we are a little bit different. So after you find that the function is continuous and differentiable, you check that f of a equals f of b. Right? So Rawls' theorem is stating that if you've got a function, it's differentiable, it's continuous, and the endpoints have the exact same value, then somewhere on that interval there's a place where the derivative equals 0. Right? So if f of a equals b, f of b, then somewhere, if all this is true, these three things, these are the three requirements, then somewhere on the interval f prime of x equals 0. There has to be a horizontal tangent. If I leave a point and I go somewhere and I come back to the same point, right, at some place I turned around. Right? So that's all Rawls' theorem is really saying in a nutshell. After you've verified it's differentiable, it's continuous and differentiable, you find, for instance, for the first one, you find f of 3 and f of 5, and you make sure that f of 3 equals f of 5. Are they the same value? If you plugged it in, you get the same number. If so, continue on. If no, then stop and say that Rawls' theorem only applies for the interval where the endpoints have the exact same value. Right? So you have to make sure they're equal. Once you've done that, you take the derivative, but now the derivative is set equal to 0, and you solve for that value of x such that f prime of x equals 0, and you make sure that c is in between a and b. All right, so after we find f of 3 and f of 5 and make sure they're the same, we find the derivative, set it equal to 0, and solve for x. Maybe you get more than one. If you get one solution, it's probably going to be between 3 and 5. But let's say you got 2 solutions, right? Let's just say you got 2 solutions. You won't on this one, but let's just say you did. You might on some other ones, like number 2. But let's say you get 2 solutions. You have to make sure you're only going to use the solutions if you get more than one, because sometimes you will. You only use the solutions that are between your endpoints, right? So only this one. If you get more than one solution, so if any solution is not between the endpoints then you'll exclude that solution. Right? That's all there is to these. Right? I didn't go over any hints on the derivatives on this one. Let me go back to Rawls' theorem. I'll give you a little hints on the derivative. Here, these ones are power rule, both of these. It's not even a chain because d, is the derivative on the inside, is 1. And then this one, you either use the product rule and quotient rule respectively, meaning product for the first, quotient for the second, or you could simplify. I don't care what you do. Either one is fine with me. They're both mathematically correct. All right. And you should be able to go between using different methods. There we go. On this group here with Rawls' theorem, you got a whole lot of power rules. They're all power rules except for 3, which was a trig, which is the derivative of cosine x. All the rest are power rules. Right? We got to rewrite the 1 over x squared as a negative exponent. Same thing with the 4 over 3x. So just make sure you rewrite function with negative exponents so that you can use the power rule. And then here, you got to rewrite that with a rational exponent. But other than that, these are all power rules all the way through. All right. Last group, second to last group, but they're kind of similar. Not that far back. This one is second derivative test and concavity. All right, so for these, this is the critical point for the we're using the second derivative test to determine increasing, decreasing. All right, so use second derivative test to determine increasing and decreasing. This video is longer than what it's going to take you to finish the homework. And decreasing. But I'm hoping that this makes it easier for you. That if you had a question, you don't have to struggle. You can practice it correctly. All right, so you find and classify the critical points. For A here, you take the derivative and set it equal to 0. And that's the first derivative. Maybe I should put that in there. right? And then to find the intervals where f of x is increasing and f of x, oh, actually I have it written down right here. Oh, and it looks nicer here. Boop. Boop. There we go. So after you find the critical points, which is where f prime of x equals 0 or undefined, there is one that has an undefined, right? You're going to test them in the second derivative, right? So you take the first derivative, you find where the first derivative is undefined or 0, and then you test those values in the second derivative. And then here is what determines whether it's increasing or decreasing. So if the second derivative is greater than 0, the point is a relative minimum. You should find, does it tell you to find and classify the critical points. Oh, this one is just increasing, decreasing. Did I put the wrong directions on this one? Well, we don't need the points. It doesn't ask for the relative max and relative min. So you could use I tell you what, use either the first derivative test or the second derivative test, because here we're not looking for oh no, it does say it for the, never mind. For the first part, I take that back. I had to think a moment. This one here, find and classify the critical points. That's this part here. I was looking at the increasing, decreasing. So the find and classify the critical points, that's where you're going to tell me whether it's a relative max and min. So there's 3 parts to this. Almost kind of ignored the A there. So for A, you're going to do this. Right? So you find the critical points, you test them in the second derivative. If the value is positive, then the point is a relative minimum. To find the y value, plug it back in the function. All right? So for A here, you're going to use the second derivative test. Not into increasing, decreasing. I don't know why I said that. Because it doesn't work so well because you're not going to know the whole interval. So use the second derivative test to find whether the critical point I put this slide together yesterday, and I guess, forgot what was on this slide. Use second derivative test to find whether the critical point is a relative max or min, and then find the y value. So that's just f of c, whatever it is, right? It's just called c, the critical point. You just plug it back in. For B and C, it actually goes together. You can do it as one part. To use a sign chart, just like you did on the first derivative of monotonicity. So use a sign chart with the first derivative. Okay, so that's for B and C. So again, in the second derivative, if it's greater than 0, it's a relative minimum. If it's less than 0, it's a relative maximum. If it stays 0 again, the test fails, and you have to use the first derivative test. Now, I don't remember if any of these fail the second derivative test or not, because I probably should have brought the key with me, but I didn't. All right, so that's this one. And the next ones, I think, are kind of similar. Is this the last one? No, second to last one. All right, so here you're finding points of inflection, concave up, concave down. All right, so you're going to take the first derivative, take second derivative. And then you're going to set the second derivative equal to 0 and solve for x. You also look for, that's not going to really come up in these ones. I don't think you're going to have to worry about where the second derivative is undefined, but I'll just put that in just for future. All right, and once you've got those, these are your critical points for the second derivative. With your critical points, you're going to make a sign chart, just like you did with the first derivative. All right, so for your sign chart, you'll have where the second derivative was 0, right? And then you'll test a value, and there might be 1, there might be 2. All right, let's just say there was 2. All right, so let's just say here we have a 0, and this other value, it's 0. All right, so you'll check the second derivative for a value less than. You'll check the second derivative for a value in between. You'll check the second derivative for a value greater. There might only be 1 critical point. There might be 2. But since there's a cube and a fourth, I would kind of think there's going to be more than 5 is going to have 1. But 4 and 6 are going to have more than 1. All right, and you make your sign chart. Now, on your sign chart, if it is greater than 0, it's concave up. Less than 0, concave down. All right? So that's how you'll determine concavity, all right, using your sign chart. That's all there is to this one. You only have to find the x-coordinate of the point of inflection, so you do not need to plug it back in. And that's it for this one. These are all power rules. How about this one over here? Power rule and a product with a chain. It has a chain rule. And this is the last one. This has all points of the inflection. If it says at points, it means x and y. Right? And to find the points of inflection, right, you don't have to tell me where it's in concave up and concave down, but you will have to take the first derivative. Take second derivative. Set second derivative equal to 0. And then also look, also check for where the second derivative is undefined. So check, you're going to, or undefined. You're going to do a sign chart, because these are the critical points. And just because something is a critical point does not mean it's a point of inflection. Right? To find where, if it's a point of inflection or not, we're going to make a sign chart. All right? And you're looking for a change in the sign chart. So there must be a change in the sign chart. In other words, positive to negative, or negative to positive for a critical point of the second derivative to be an inflection point. All right, once you got that, then find so it could be undefined. This is undefined for the second derivative here. It could be undefined for the second derivative, but just fine for the first derivative. If it is undefined for the not first derivative, excuse me, for the original function. If it is undefined for the original function, it is not an inflection point. So you're going to find the y values for x where f double prime of x equals 0, or f double prime of x equals undefined. Right? And then by substituting into f, the original function. Or y, apparently. Two of them have to be y's. And you're substituting, of course, for x. Right? And that is all there is to these. In terms of the derivatives, you've got the product rule. The next one is a product rule or simplify. You got arctan, and this one is a quotient rule. All right, and that's all there is to this homework. Thanks for watching. If you have any more questions, let me know. And we have a blank page, but that's the end of this video. Bye for now. Have a great day.